Welcome and thanks for joining my talk. I'm Martine and together with my colleagues Cenk Gündoğan, Thomas Schmidt and Matthias Wählisch, we worked on integrating the emerging IETF standardization around fragment forwarding and selective fragment recovery into ICNLoWPAN. ICNLoWPAN is the ICN adoption layer for low power and lossy networks currently proposed within the IRTF. First, I will talk about our motivation and give a short introduction on fragmentation within ICNLoWPAN. Then I will present you our proposal to address the problems we encountered in form of the so-called Virtual Reassembling Endpoint. For the Virtual Reassembling Endpoint, I will then provide you with our evaluation and compare it to established approaches within ICNLoWPAN. Last, I will conclude my talk and give you an outlook on our future work. So, the first question you might ask yourself is, why do we need fragmentation in ICNLoWPAN at all? Well, if we look at the classic internet, we encounter PDUs that usually provide us with more than enough space to carry all the information we need. When looking at the embedded IoT, however, we face PDUs of only a few hundred bytes. To be able to communicate with the wider internet regardless, ICNLoWPAN introduces both header compression and fragmentation, the latter of which will be the focus of this talk. However, the rules of fragmentation and reassembly are different in ICNLoWPAN, as you might know it from other protocols such as IP fragmentation. Since the forwarding information is only carried in the first fragment in ICNLoWPAN to save space, a decision needs to be made for how to forward fragments. The classic and naive approach is hopwise reassembly. Here, when the first fragment arrived, it is added to the reassembly buffer that is then filled up with subsequent incoming fragments which are identified by the link-specific datagram tag until the full datagram is reassembled. When the network layer then comes to the conclusion to forward the packet, it is refragmented again. However, this approach wastes a lot of memory, as we need to allocate enough space to hold every datagram that is incoming. Given that on the type of nodes we are working with in the IoT, we only have a few kilobytes of memory, this can lead to a forwarding bottleneck. Alternatively, we can forward fragments directly by utilizing the so-called virtual reassembly buffer to associate the datagram tag with the forwarding information. Here, when the first fragment arrives, we look up the forwarding information in the network layer and create a virtual reassembly buffer entry based on that. This way, we don't have to store the whole datagram for forwarding, saving resources. The incoming fragments are then forwarded directly without any reassembly. Compared to hopwise reassembly, this can be implemented with only a few bytes of memory in RAM. In both cases, however, we face the problem that if only one fragment gets lost, the whole datagram is lost and might need to be retransmitted by an upper layer. For this, Selective Fragment Recovery was introduced, where for a collected number of received fragments, the window size, a cumulative acknowledgement message is sent by the reassembling endpoint. The accumulation of acknowledged fragments is achieved by using sequence numbers in the fragments and a bit mask in the ACK where each bit represents a completed fragment with a sequence number equivalent to the position of the bit. In the given example, the fragments with sequence numbers 1 and 2 are acknowledged by the first 2 bits in the ACK being set. Using a reverse lookup in the virtual reassembly buffer, this acknowledgement can be forwarded by intermediate nodes to the fragmenting endpoint. When the acknowledgement signifies that a fragment is lost, the fragmenting endpoint has a chance to resend only the lost fragment, which is then forwarded and the acknowledgement returned as before. Another ICN-specific problem when forwarding fragments is that while with hopwise reassembly, the forwarder sees the completed datagram at some point in the process and thus enables ICN to add the completed content chunk to its content store, direct fragment forwarding, however, does not allow for that. ICN uses content chunks, but since they are fragmented datagrams, we never see the full chunk. In turn, we are not able to cache forwarded content chunks when directly forwarding fragments, but is there maybe a way to have the advantages of both? When we look at the requirements for that, we of course want to fulfill the two identified advantages first. So we want to make the full content chunk available to an ICN forwarder. even if fragment forwarding is used, and be as frugal with memory as direct fragment forwarding is. As such, should our implementation mostly reuse existing data structures and only slightly extend them. Additionally, it should be compliant with the given standards, meaning that our proposal should be transparent to the network. The cached fragmented content chunk should behave like any other content chunk, but should be unable to poison the network with incomplete data. In our proposal, the Virtual Reassembling Endpoint extension, short VREP extension, the content chunk is reassembled tentatively en route to in the content store. Such a tentative content store entry, however, is not served to incoming interest as per our requirements. So only if the datagram was fully acknowledged, the content store is made available to incoming interests. Another benefit with this approach is that if the acknowledgement is indicating a loss, this fragment can be restored directly from the content store and act according to the fragmenting endpoint if the fragment information is retained. To evaluate our proposed virtual reassembly buffer extension, we compared 3 approaches to fragment forwarding. Classic hopwise reassembly, which in our results we abbreviate as HWR. Classic selective fragment recovery without the virtual reassembling endpoint extension, short SFR without VREP. And finally, selective fragment recovery with our proposed extension, short SFR with VREP. We picked 2 topologies based on previous experiences. A daisy chain topology that consists of 7 hops between the consumer C and producer P to benefit caching behavior, and a Y topology that consists of 1 consumer C and 2 producers P1 and P2, with the consumer and producer separated by 2 hops F1 and F2. Note that F2, the forwarder closest to the producers, forms the previously discussed bottleneck. For the sake of time, I'd like to ask you to look up further setup and configuration parameters in our paper, please. First, let's have a look at the time to completion, or TTC for short. You can see 2 CDF plots, 1 for each topology, with a time to completion in seconds on the x-axis and the CDF on the y-axis. The datasets for HWR are represented as an orange line, for SFR without VREP as a blue line, and for SFR with VREP as a green line. Note that for the daisy chain topology we added a zoom in, as the completion rate never becomes greater than 3%. For the Y topology, we did not see any successful completed requests with SFR without VREP, which is why we do not see any CDF for it in the right plot. But also, in the daisy chain topology, we see only less than 1% of the requests completed. So, selective fragment recovery without the virtual reassembling endpoint extension performs completion-wise bad in both topologies. For the daisy chain topology, hopwise reassembly performs slightly better than selective fragment recovery with the virtual reassembling endpoint extension, but comparable. In the Y topology, however, SFR with VREP performs much better, twice as good as hopwise reassembly. Since we pre-configured the window size for our experiment statically to 1, HWR always has a slightly shorter TTC than both SFR variants, as SFR requires an ACK exchange in addition. We picked this window size to reduce noise, since the minimal congestion control mechanism proposed in the draft always ended up at 1 in our setup anyways. Looking at the content store hits, so when an interest is served by the cache rather than the producer application, we only compared the behavior within the daisy chain topology. The figure you can see plots the nodes within the network, consumer C and forwarders F, 1, 2, etc., marked on the x-axis. F6 is closest to the producer, F1 is closest to the consumer. The number of content store hits at each of the nodes is on the y-axis. Hopwise reassembly is seen in orange bars. Selective fragment recovery without the virtual reassembling endpoint extension in blue bars, and selective fragment recovery with the VREP extension in green. In general, both SFR variants experience less cache hits closer to the consumer, which leads to an increased content store access at the producer. As the SFR implementation used in our experiments falls back to hopwise reassembly when the reassembly buffer is full, We also contrasted the cache hits with the number of events when the VRB is full in a scatter plot to better understand the impact of that behavior. In this scatter plot, we see three clusters. The one on the left represents all results for SFR with VREP, which mostly bunch up on the y-axis. The two on the right represent the SFR without VREP dataset for forwarders 5 and 6, so the ones closest to the producers. From these plots, we can see that the cache hits with SFR without VREP solely come from the SFR fallback, while for SFR with VREP, they come from the Virtual Reassembling Endpoint extension. In summary, our evaluation shows that the proposed Virtual Reassembling Endpoint extension for Selective Fragment Recovery fulfills the requirements we set for it. It saves memory by reusing existing data structure and additionally is serving the full content chunk to ICN forwarders. It also shows that using SFR without the VREP extension yields the worst results in any case. For topologies with many hops without intersection points, hopwise reassembly has a slight advantage over selective fragment recovery with the VREP extension, though negligible. However, when there are intersection points in the network, those will form a bottleneck in the reassembly buffer of hopwise reassembly. Here we get significantly better results for SFR with the VREP extension over hopwise reassembly. For our next steps, we plan to analyze the impact of the Virtual Reassembling Endpoint extension with more complex MAC layers, such as IEEE 802.15.4, also known as TISH, different congestion control mechanisms with SFR, and different ICN caching strategies. Thank you for your attention. If you have questions, please ask them. I can give you, however, already an answer I'm sure many of you are burning to have answered. Is our research reproducible? And I can say yes. You can find all the code of our experiments both on GitHub and the ACM digital library.